As the blazing midday sun scorched the New Mexico desert, America's scientific elite gathered together to watch the assembly and installation of a strange-looking device. The machine Oppenheimer, Teller, and Fermi were there to see was codenamed Gadget, a 2-meter metal sphere that seemed to be growing cables from every orifice. Beneath its steel outer shell, layers of explosive lenses, and a uranium tamper sat a small core of just 6 kilograms of plutonium. This grapefruit-sized metal sphere was enough to set the world on fire. As the sweat-drenched team watched, Gadget was winched up a 100-foot tower. The gravity of the moment was felt by all. The culmination of the work of some 130,000 people over 3 years and billions of dollars of investment was slowly ascending that tower. To everyone's horror, Gadget became unhinged and nearly fell, but disaster was averted when a member of the crew stabilized it. If the device failed, much of that effort would have been for naught. If it worked, the most harrowing war in human history might be finally brought to an end. The time for detonation was set at 4 a.m. Monday, July the 16th, 1945. However, as H hour approached, a nearby thunderstorm delayed the test until 5:30. To cut the tension, Fermi began taking bets on whether or not the bomb would ignite the atmosphere, and if so, whether it would merely destroy New Mexico or destroy the world. Oppenheimer was happy to wager $10 against George Kistiakowski's entire month's pay that the bomb would not work at all. As the final minutes ticked down, most observers lay down on the desert floor to shield themselves from the blast, despite the fact that the observation area was several miles from ground zero. At precisely 5:30, the pitch-black darkness was illuminated by a blinding light, so bright that even to look at it would mean near-certain blindness. Witnesses described the surrounding hills as being as perfectly illuminated as if it were lit by the midday sun. As the brilliant white light receded to a fiery orange, the crowd rose to view a mile-wide fireball rise silently into the desert sky. Beneath it, a stem of dust and debris connected the rising cloud to the earth below, the iconic phenomenon of a nuclear explosion. As the onlookers began to cheer, the shockwave reached them, a deafening blast that carried loose paper several meters away. The blast was so powerful that it knocked over a 200-ton steel container that was over half a mile from ground zero. Oppenheimer, one of the leading scientists in the Manhattan Project, later recalling the moment, quoted the Hindu sacred text, the Bhagavad Gita, "Now I am become death, the destroyer of worlds." Humanity had now entered the nuclear era. The power unleashed by the Gadget device was preposterous. Despite only weighing a few tons in total, with a core of just 6 kilograms of plutonium, the Trinity test unleashed an energy equivalent to 24,800 tons of trinitrotoluene, or TNT. To put that into perspective, an Iron Duke class battle
Gadget was the first nuclear device ever detonated. Contained, what was it, 6 kilograms? Is that what it said? Of plutonium? What was the year for this? $1945.
Battleship displaced around 25,000 tons of water at a light load. In order to achieve the same energy release, one would have to amass a pile of high explosives that weighed as much as a World War I super dreadnought battleship. But how could such a thing even be possible? What kind of demon hid inside that 6-inch sphere of radioactive metal that could destroy a whole city? To understand nuclear weapons, and what makes them so unfathomably powerful, we have to not only examine how they work and how they kill, but the fundamental constituents of matter and energy. Human warfare has been dominated by explosives for over 500 years. Black powder, a combination of sulfur, saltpeter, and charcoal, revolutionized combat, allowing for the dominance of firearms and artillery, the foundational arms of armies to this day. Black powder releases energy by rearranging chemical bonds. It contains both fuel and oxygen, which are both stored in solid form. When ignited, both are released simultaneously, allowing an extremely rapid combustion to occur without the inclusion of external oxygen from the atmosphere. This is called a deflagration. This process rapidly converts all of the solid to a gas, which, as gases are far less dense than a solid, generates a small area of extremely high pressure and temperature. Given the fact that a local area of high pressure will always move towards equilibrium, this highly compressed hot gas expands extremely rapidly, generating a highly destructive blast wave.
What debate is going to come and use? I always have questions about nukes and nuclear stuff and everything. So why not just watch a 2-hour thing on it, learn some stuff, take some notes. It's good. Not everything has to be for a debate or test, okay? Just general knowledge.
This phenomenon is exacerbated by explosives that combust at supersonic speed, which are called high explosives. C4 and TNT are two famous high explosives. In simple terms, chemical explosives rely upon the energy stored in chemical bonds. Chemistry is driven by the interactions of different molecules, which are nothing more than the arrangements of different chemical elements, such as carbon or oxygen, that are bonded together in certain well-defined ways. The smallest chemical element is an atom, which are bonded together to form all of the molecules of the universe. Chemical bonds are driven by the interaction of an atom's electrons. Of different chemical elements, such as carbon or oxygen, that are bonded together in certain well-defined ways. The smallest chemical element is an atom, which are bonded together to form all of the molecules of the universe. Chemical bonds are driven by the interaction of an atom's electrons. If two atoms share a value called electronegativity, they will share electrons, forming a covalent bond. Atoms with high electronegativity can become attracted to each other if they are of different electrical charge, which creates ionic bonds. Typical high explosives leverage chemical reactions like combustion to unleash the energy stored in these chemical bonds by rearranging the molecular structure extremely rapidly. Nuclear energy is very different. Rather than relying upon the rearrangement of chemical bonds, nuclear reactions leverage the forces that bind atoms together. As stated previously, molecules are arrangements of atoms. However, atoms themselves are simply arrangements of subatomic particles that are bound by their own nuclear forces. An atom is made up of three foundational constituents: protons and neutrons, which are bonded to form a nucleus, and electrons which orbit around the nucleus. This view of the atom is highly simplified, as according to quantum mechanics, the electrons do not orbit the nucleus, but rather exist in a cloud of possible locations that are governed by a wave function, but for our purposes this Newtonian view of the atom will suffice. Within the nucleus, the protons and neutrons are composed of a more fundamental element called a quark, 3 in each. The proton, which contains 2 up quarks and 1 down quark, is positively charged. The neutron, as the name suggests, has no charge and is therefore neutral, and is composed of 2 down quarks and 1 up quark. Electrons are negatively.
Wait, why is a neutron 0? Or is it just saying... Am I retarded? The neutron is made from 2 down quarks and 1 up quark. The charge is cancelled to make 0. Why?
Charged is positively charged. The neutron, as the name suggests, has no charge and is therefore neutral, and is composed of 2 down quarks and 1 up quark.
Why wouldn't it be negative? Why wouldn't it be negative 1? Oh, it's a different charge on the quark. Oh, never mind. Just kidding. Okay.
Electrons are negatively charged. The simplest atom is hydrogen, which has a nucleus containing a single proton. As the nucleus is charged, it will attract a single electron, making the atom as a whole electrically neutral. The different chemical elements like helium, oxygen, iron, and carbon are simply defined by the number of protons that are in the nucleus. Helium has 2 protons. Oxygen has 8. The higher the atomic number, the more protons an atom contains. In addition to protons, the nucleus of an atom can contain differing numbers of neutrons. As neutrons are neutral, the number of these has no effect on chemical reactions. This means that a single chemical element, like hydrogen, can have different masses by having different numbers of neutrons accompanying the proton. For example, deuterium is simply hydrogen with 1 additional neutron, and tritium is hydrogen with 2 neutrons. Water that is composed of oxygen and deuterium is called heavy water for this reason. Oxygen, as an example, has 3 primary isotopes, the most common of which is oxygen-16, which contains 8 protons, like all oxygen atoms, and 8 neutrons. Unlike the bonds of chemistry that rely on electrometons, like all oxygen atoms, and 8 neutrons.
The number at the end denotes the atomic mass, which is usually for added neutrons, almost always, right? That's right?
Unlike the bonds of chemistry that rely on electromagnetism, the nucleus is held together by the strong nuclear force.
Cringe.
One of the 4 primary forces of nature, this is the interaction that binds up and down quarks together, and this force leaks out of the protons and neutrons to bind them as well. The strong force is strong, really strong.
Wow.
Over the size of an atomic nucleus, it is 137 times stronger than electromagnetism.
Wow.
It is much stronger than that within a proton or a neutron, but much of this force is cancelled out within the particle itself, and thus only a small residual amount escapes to bind the atomic nucleus together. Despite its strength, the strong force is extremely short-ranged. Subatomic particles will only feel its effect if they are extremely close together. Just as chemical explosives leverage chemical reactions like combustion, nuclear explosives rely on nuclear reactions. Sometimes...
Wait, why is that? Is this like reverse square law stuff, or does it fall off in like a different way that's different than that?
Leverage chemical reactions like combustion, nuclear explosives rely on nuclear reactions. Sometimes one chemical element will change into something else.
Different way. Inverse square law, sorry. That's just how it was programmed. Oh, okay. That was the program, my bad.
When this happens by itself, we call this process decay. Generally speaking, atoms will always change to rely on nuclear reactions. Sometimes one chemical element will change into something else. When this happens by itself, we call this process decay. Generally speaking, atoms will always change into something more stable, and in undergoing that transformation, they will release radiation. This is why this process is called radioactive decay. There are two other relevant nuclear reactions, fission and fusion. Fission occurs when a very heavy atom, such as uranium, splits into smaller pieces, usually two halves, each of which will now become a new, lighter atom. When a heavy atom undergoes fission, it releases a significant amount of energy in the form of radiation and kinetic energy. Fission can be triggered by hitting a heavy atom with a neutron, however it can also occur spontaneously as a result of radioactive decay. The other type of nuclear reaction is fusion. This occurs when two
For radioactive decay, do elements decay into other elements? Because if you're just losing a neutron, how do you change elements? Wouldn't you have to lose like a proton or something? Or an electron? Not or a proton? There are different forms of decay. An unstable atomic nucleus loses energy by radiation. Unstable nuclei is considered radioactive. Okay, I don't think I care about this so much.
as a result of radioactive decay. The other type of nuclear reaction is fusion. This occurs when two very light atoms, such as hydrogen, fuse together to form something heavier, such as helium. In order for fusion to occur, the two atomic nuclei have to get close enough to feel the strong forces of attraction. But in order to do so, they have to overcome the electromagnetic repulsion felt by two bodies of the same charge.
Wait, okay, I need to be in brain absorbing mode.
In order for fusion reaction is fusion, result of radioactive decay. The other type of nuclear reaction is fusion. This occurs when two very light atoms, such as hydrogen, fuse together to form something heavier, such as helium. In order for fusion to occur, the two atomic nuclei have to get close enough to feel the strong forces of attraction. But in order to do so, they have to overcome the electromagnetic repulsion felt by two bodies of the same charge. This means enormous temperatures and pressures are required to initiate fusion. This reaction also releases vast amounts of energy, and it is the very mechanism that powers the sun. So, by rearranging subatomic particles to create new atoms, rather than rearranging atoms to create new molecules, nuclear explosives leverage a force of nature that is well over 100 times stronger than their chemical counterparts. When we account for just how many more atoms there are than molecules, this leads to reactions that are tens of thousands of times more energetic. As an example of just how much energy is released in a nuclear reaction, if just 1 kilogram of uranium undergoes complete fission, this will release the same energy as 17.5 kilotons of TNT. Because of how difficult it is to initiate fusion, the first nuclear bombs relied purely on fission as a nuclear reaction. Nuclear energy, whether it is released in a nuclear reactor or an atom bomb, rests on the fact that when some atoms undergo fission, they release more neutrons than they absorb. If enough neutrons are released, this allows the possibility of a chain reaction. One atom is hit by a neutron and splits, releasing 2 more neutrons. If these hit another nucleus, these will, in turn, undergo fission, releasing 4 additional neutrons, which can then go on and hit more atoms. This is called a chain, or self-sustaining, reaction. A nuclear power plant is simply a very well-controlled chain reaction that occurs very slowly, releasing energy in a predictable and manageable way. But when this chain reaction occurs in a highly compressed pit of fissile material, it can happen extremely quickly, releasing an ungodly amount of energy in the process. Nevertheless, there are a few problems. The first issue is the fact that there are very few chemical elements that can sustain a chain reaction, or, to be more precise, only a small number of isotopes of these few chemical elements. Uranium is the heaviest natural chemical element that is reasonably abundant on Earth, but the vast majority of it is incapable of sustaining a chain reaction. Over 99% of all known uranium deposits are U-238, which can undergo fission if hit with a fast neutron, but won't release enough neutrons to sustain a chain reaction.
What is uranium normally on the... The atomic number denotes the amount of protons, right? (146 neutrons). So when you're talking about the isotope of a thing, so U-238 denotes an isotope. So what, the isotope is the protons and neutrons added together? What am I thinking? Oh. Do atoms tend to have the same number of protons and neutrons? They do, right? They tend to have the same number, or is it just the same number of protons and electrons? Yes, typically. Sometimes. Only small atoms. Okay, it starts to deviate. Yeah, because atomic mass or weight gets weird at higher numbers. So would you say there's like a naturally occurring isotope, or is the naturally occurring thing not considered an isotope? There's naturally low concentration. Uranium is used in nuclear weapons because it is the only naturally occurring element with a fissile isotope, uranium-235, present in non-trace amounts. So most of it is uranium-238. Okay. How does it... I don't know. Maybe it'll say. Why are some of them 235 and some of them 238? Do they get like... Do they just like pick up or lose protons? I guess through random radioactive decay or whatever, huh? Whatever, okay.
The only naturally occurring fissile isotope is U-235, which accounts for just 0.72% of all uranium. These two isotopes are evenly mixed throughout the world's uranium deposits. The reason there is so much less U-235 than U-238 is because it has a significantly shorter half-life, making it a little more radioactive. Most of it has simply decayed. Extracting U-235 from U-238, a process called enrichment, is an extremely difficult engineering challenge. Because both are isotopes of uranium, you cannot use chemistry to do it. Generally speaking, enrichment processes rely on the minute difference in weight between the two isotopes in order to separate them. In 1944, uranium tetrachloride, a chemically stable form of uranium, was heated until it formed gas, ionized, and then spun in an electromagnetic field. The heavier U-238 ions would then be pushed to the outer edge of the container, separating the isotopes. Gaseous diffusion was another method utilized, but today centrifuges are used for this purpose. Enrichment is an expensive and extremely time-consuming process. In order to achieve a nuclear detonation, the fuel has to be enriched to 90% uranium-235, which means removing the vast majority of the U-238 from uranium ore. The waste product of this process, which is just U-238, is called depleted uranium. Because of its immense density and low radioactivity, depleted uranium makes excellent armor and armor penetrators. This whole process made up the vast majority of the Manhattan Project's cost. Over 30,000 people worked at the massive enrichment plant at Oak Ridge, Tennessee, and after 2 years of effort, they only had enough U-235 to make a single nuclear weapon. Nonetheless, there are other ways to create fissile material. Although uranium is the heaviest, widely occurring natural element that exists on Earth, heavier atoms can be created in a nuclear reactor. These elements are called transuranics, and include neptunium, plutonium, americium, californium, and even einsteinium, which was named after Albert Einstein. Some of these heavier elements, which contain more protons than uranium, can sustain a fission chain reaction in exactly the same way as U-235, and it is for this reason that plutonium has become famous. Reactor fuel has to be enriched in the same way as the uranium used in a nuclear weapon. Elements, which contain more protons than uranium, can sustain a fission chain reaction in exactly the same way as U-235, and it is for this reason that plutonium has become famous.
What was uranium? 92. Oh, cool. Wait, what's atomic number 93? That guy doesn't get any love.
Reactor fuel has to be enriched in the same way as the uranium used in a nuclear weapon, but to a much lower degree. In fact, some reactor fuel may only contain 5% U-235, meaning the majority of the fuel is still U-238. When a nuclear reactor is operational and fission is occurring, copious amounts of neutrons are produced. Occasionally, one of these will hit a U-238 atom, and when this happens, there is a reasonably good chance that said neutron will simply be captured. Because we just added an additional neutron to the nucleus, this creates an isotope called U-239. But U-239 is very unstable. It rapidly undergoes a pair of beta decays, in which one of the atom's neutrons turns into a proton, emitting an electron in the process. As this changes the number of protons, a heavier element is created. First, U-239 changes into Neptunium-239, which then rapidly undergoes the same process and decays into Plutonium-239. All of these isotopes have the same mass, it's just that the numbers of protons and neutrons have changed. Creating plutonium in a nuclear reactor essentially alleviated the requirement to undertake extremely difficult and expensive isotopic separation. Because plutonium is a different chemical element, it can be separated from the uranium fuel by a simple chemical reaction, greatly reducing the costs of nuclear weapon production. Plutonium-239 is also a superior fissile material compared to U-235. It has a higher chance of undergoing a fission when hit with a neutron, and releases more neutrons per fission, meaning you need much less to achieve critical mass. The only issue with plutonium is an isotope called plutonium-240, which can be created when plutonium-239 absorbs a neutron. Plutonium-240 is a poison for nuclear weapons. It is highly radioactive, making it dangerous to work with. It is also prone to spontaneous fission, making a weapon likely to detonate with a suboptimal yield, something called a fizzle. For this reason, weapons-grade plutonium is defined by the amount of plutonium-240 it contains, below 7% for military purposes. Typically, spent fuel that has been in a nuclear reactor for 3 years will contain around 40% plutonium-240, making it very unsuited to use in nuclear weapons. Military breeder reactors will typically only expose the fuel for 3 months, limiting plutonium-240 production. The tendency of even a small amount of plutonium-240 to create a fizzle event has significant consequences for nuclear weapon design. A key concept to understand in nuclear engineering is something called a critical mass. In essence, this is the amount of fissionable material required to achieve a chain reaction. Basically, even if you successfully start a fission, or one just happens due to decay and 2 or 3 neutrons are released, if there aren't enough other nuclei around, the chances of getting another hit will be less than 1, making a chain reaction impossible. This is called a subcritical mass. However, if you pile up enough fissile material in one place, the chances of getting a hit with each neutron release will be greater than 1, simply because there are more fissile atoms around, meaning for every fission event, you get at least one other fission. For U-235, a critical mass for a sphere at normal density is about 47 kilograms in weight. For plutonium-239, the same sphere needs to be about 10 kilograms. There are 2 primary methods by which a critical mass can be reduced. The first is by using neutron reflectors. If you surround the core with a substance that will cause neutrons to bounce off it, like graphite, you effectively double the chance that any neutron will hit an atomic nucleus before it escapes.
Holy shit, Chernobyl.
The other way to
Anybody
reduce
watch
the
that TV
critical
show?
mass is by compressing the material. If you bring the uranium or plutonium atoms closer together, effectively making the material look thicker to a neutron, you also increase the chances of scoring a hit. In the simplest of terms, nuclear weapons work by taking a subcritical mass of fissile material and making it critical as fast as possible. Obviously, if one were simply to make a critical mass by piling up enough U-235, you would not accomplish anything other than your own annihilation. There are a couple of ways to do this. The first is to take 2 subcritical masses that are large enough that they would be critical if they were in the same place, and simply bring them together. This was the design used by the Hiroshima bomb, the first nuclear weapon used in war. Codenamed Little Boy, This device used a gun barrel to bring two chunks of highly enriched uranium together. Inside the bomb sat a smoothbore artillery barrel that was 1.8 meters long and 165 millimeters, or 6.5 inches, wide. At one end sat the target, a small, 4-inch wide and 7-inch high cylinder of highly enriched uranium that weighed some 25 kilograms. At the other end, in front of a high explosive charge, was the projectile, a cup-shaped mass of uranium that was backed by a tungsten carbide pusher. When the weapon was detonated, the explosive charge accelerated the 38-kilogram projectile down the barrel at several hundred meters per second. The target and projectile were designed so one would fit inside the other, rapidly creating a supercritical mass. At the base of the weapon, the uranium target was surrounded by a tungsten carbide tamper. A tamper is a critical element in nuclear weapon design. Essentially just a very dense material that surrounds the core, a tamper significantly improves the efficiency of the weapon by slowing down its expansion during detonation, allowing for additional chain reactions before the bomb blows itself to pieces. This tungsten carbide tamper also acted as a neutron reflector. The gun type is by far the most simple form of nuclear weapon design. It is essentially foolproof. It was deemed to be so reliable that no full-scale test of the little boy weapon was required, although there was only enough weapons-grade uranium for a single device anyway, an indication of just how difficult uranium enrichment is. Nonetheless, this kind of design has many significant limitations. The first is its very low efficiency. Despite being accelerated down the barrel at hundreds of meters per second, it is very hard to avoid the initiation of the nuclear detonation before the two halves have completely integrated. A key challenge in nuclear weapon design is the fact that a supercritical mass will instantly want to blow itself to pieces, stopping the chain reaction. If this happens too quickly, the yield will be low, causing a fizzle. Even in the most efficient weapons, only a fraction of the fuel undergoes fission. The problem with the gun-type weapon is fission will virtually always initiate too early, leading to low yields. Little Boy contained 64 kilograms of fissile material, nearly 3 critical masses when you account for neutron reflection, yet...
Thoughts on Israel undermining the deal for the entire duration of it being up before Trump breaking it? What, the Iran nuclear deal? Israel doesn't want the Iran nuclear deal. Israel doesn't like Iran. Israel wants the Iranian regime to collapse. Like, they were mad. Israel was ultra ass-pained when Obama signed that nuclear deal. Israel's not a fan of Iran, and they don't want them to reach a nuclear deal with the United States. That's been the case for as long as I'm aware.
It was a fissile material to low yields. Little Boy contained 64 kilograms of fissile material, nearly 3 critical masses when you account for neutron reflection, yet only 1 kilogram of uranium actually underwent fission, generating a neutron reflection, yet only 1 material, nearly... Little Boy contained 64 kilograms of fissile material, nearly 3 critical masses when you account for neutron reflection, yet only 1 kilogram of uranium actually underwent fission, generating a yield of some 16 kilotons. This issue also means a gun-type design is unsuited to plutonium. Even weapons-grade plutonium contains a small amount of plutonium-240. Because this isotope constantly emits significant levels of neutron radiation, it will almost certainly cause a fizzle, leading to a very low yield. To avoid these limitations, the Manhattan Project scientists leveraged the other way you can safely turn a subcritical mass of plutonium supercritical: compression. But how do you highly compress one of the densest metals that exist? Well, you can use high explosives. Basically, if you take a sphere of plutonium and surround it with a larger sphere of explosives, you can compress the metal enough to make it supercritical. But this is far more difficult than it seems. Firstly, you have to use something called an explosive lens, which is a specially shaped blend of different explosive compounds that is designed to focus the shockwave in the same way as an optical lens focuses light. The plutonium core has to be surrounded by these lenses, which all have to be detonated within milliseconds of each other. If the detonation is not nearly simultaneous, the core will not be sufficiently compressed, leading to a fizzle or even a non-detonation. The electronic requirements of an implosion design were absolutely state-of-the-art in 1945. It was just barely possible given the technology of the age. The Gadget device, which was all but identical to the Fat Man bomb dropped on Nagasaki, was a highly complex machine.
Why is it so hard for Iran to get nukes? I don't know! That's why I'm watching this. I don't have a fundamental understanding of nuclear weapons. It's less than 2 hours long, okay? You can do a whole college course on nuclear physics and more, okay? Just we're watching to understand, all right? My understanding going into this, and maybe it'll change by the end of it, I don't know. My understanding is that the centrifuges, the technology required to enrich like uranium to a weapons grade level, there is not a shortcut or an easy way to do that. It just requires huge fucking machinery, and it requires a fuck ton of energy, and you just have to, I don't know if the centrifuges, they're called centrifuges, I don't know if they actually spin shit, but it's a lot of power to separate out these things. There is no like mini super efficient Elon Musk device that can just enrich uranium. That's just a process that's annoying and energy intensive, and it requires huge machinery to do it. So in order to do it, like that's why you can't do it secretly. People generally know, and it's a difficult, arduous process that is annoying as fuck to embark on. That's my understanding. But I don't know. Maybe it'll change my into this. We'll see.
At its core was a plutonium pit that was just over 9 centimeters, or 3 inches, in diameter and weighed 6.1 kilograms. Made up of 2 hemispheres, the plutonium pit contained a small initiator at its center. An urchin made of beryllium and polonium. This initiator would release a powerful burst of neutrons when crushed, aiding in the detonation process. Encasing the pit was a 13 centimeter thick tamper that weighed some 111 kilograms. Unlike the little boy weapon, which could not permit any stray neutrons near the target, this tamper was made out of depleted uranium. Not only would this very dense metal slow down the explosion, but U-238 is also capable of undergoing fission if struck by a high energy neutron, meaning the bomb as a whole would have a greater yield. In fact, about 30% of the total energy came from the fission of the uranium tamper. Outside of this metal sphere, 32 explosive lenses were arranged to form an even larger 1.5 meter sphere. When triggered, the weapon's electronics initiate the explosive lenses through exploding wire detonators, which had to be invented for the project. As the nearly 2 tons of high explosives detonate, a supersonic blast front is formed and focused by the shape of the charges, compressing the plutonium pit. With the core rapidly becoming supercritical, it is showered by neutrons from the initiator at its center, which augment the
There's a 5-minute YouTube video that explains the different... Okay, I'm sorry, hold on. Somehow, so one day, we will purge the weak. There's a 5-minute YouTube video that explains the different enrichment process in a lot more detail than the current video you're watching. I don't know how much nuclear physics I remember from high school, okay? I couldn't tell you anymore. They're just like alpha decay, beta decay. I don't remember anymore, okay? So when you watch this, to get a general understanding, so that when I'm talking about a topic, when you talk about a topic, you don't want to just repeat every single thing you know, and that's all you know in 5 minutes, okay? You have build up a soft background. It's less than 2 hours, just to have a somewhat of an understanding of the topics, and then you can watch more specific videos. That's how I like to learn things, okay? Stop triggering me. Stop doing it. You're triggering me intentionally. I know you're trying to trigger me. Stop.
Constantly occurring natural fissions. These reactions happen extremely quickly. A generation of fissions occur roughly 100 millionth of a second, or 0.01 microsecond. From a single neutron, it will take 51 generations of fission reactions to generate a 0.1 kiloton yield. However, because of the exponential growth in the number of neutrons, with the number of reactions more than doubling every generation, 100 kilotons is achieved in just 58 generations. This means that the vast majority of the energy generated is released in the last 7 generations, or about 0.07 of a microsecond. At this point, despite the influence of the heavy tamper, the temperatures inside the weapon are so high that the atoms of plutonium begin to move away from each other at tremendous speed, ending the reaction. The Fat Man proved to be a far superior weapon design to the Little Boy. Despite using just 6 kilograms of fissile material compared to 64, which was the much easier to produce plutonium-239, it generated a significantly larger yield of just over 20 kilotons. About 1 kilogram of plutonium underwent fission, generating a yield of roughly 15 kilotons, achieving a 16% efficiency. This was the same amount as Little Boy, however that weapon utilized 10 times more fissile material. Additionally, the ability to use a depleted uranium tamper added another 5 to 7 kilotons. The Little Boy was also a seriously unsafe weapon. Once the cordite charge was loaded, if it detonated for any reason, a full yield explosion would inevitably result. Additionally, as there were two subcritical cores present, even if the bomb was dropped from an altitude of 15,000 feet without being armed, the impact of hitting the ground would have been enough to cause a serious nuclear detonation. A similar threat was present when flying over water. The sheer volume of fissile material, nearly 3 critical masses, meant that if seawater entered the weapon, it would act as a moderator, slowing down the neutrons and making fission more probable. This alone could make the weapon supercritical. None of these issues were present with the Fat Man design. Even if one or more of the explosive lenses exploded prematurely, this would not cause a nuclear detonation. Only the very precise, simultaneous detonation of all 32 lenses would generate the required compression of the pit. This is basically impossible unless you mean to do it. Additionally, because there simply isn't a critical mass of plutonium unless it is compressed, none of the other risks are really a factor. In essence, the implosion mechanism remains the same for all modern nuclear weapons to this day. The Fat Man design became the mainstay of the first generation of both American and Soviet nuclear weapons, as the first Soviet bomb was based on technical information provided to the KGB by Los Alamos scientist Klaus Fuchs, and was thus a direct copy. This design led to the Mark III and Mark IV freefall bombs, which could achieve yields of between 1 and 30 kilotons depending on the type and size of the pit installed in the weapon. By the early 1950s, research began into incorporating the fusion reaction into nuclear weapon design. Even in the 21st century, a fusion reaction is extremely difficult to initiate and sustain, but with working fission weapons, the requisite temperatures and pressures could now be reached. One of the first ways this new reaction was implemented was through a process called boosting, a term coined by Edward Teller. In this process, a very small amount of heavy hydrogen isotopes, tritium and deuterium, were injected into the center of an enriched uranium pit of an implosion bomb. When the fission reaction began, the deuterium and tritium were exposed to unimaginable pressure, enough to initiate fusion, converting both into helium-4. The additional blast yield from this reaction was minimal. However, the deuterium-tritium reaction releases a vast number of fast neutrons. With this shower of additional neutrons flowing through the core, the number of fissions that occurred before the bomb blew itself to pieces was vastly increased. This improved the efficiency of the weapon, doubling the amount of material that actually underwent fission. The boosting technique was first tested during Operation Greenhouse in 1951. Shot Item was the first demonstration of a boosted weapon. Just via this technique, the yield of the bomb was doubled to 45.5 kilotons. With the success of the Greenhouse Item test, which had demonstrated that the detonation of an atom bomb could produce the required conditions to initiate nuclear fusion, work began on a device that could create fusion on a much larger scale. Fusion is a highly attractive nuclear reaction. Weight for weight, the fusion of deuterium nuclei produces nearly 3 times as much energy as the fission of uranium or plutonium. The critical development was the immensely high temperatures generated by a runaway chain. Weight for weight, the fusion of deuterium nuclei produces nearly 3 times as much energy as the fission of uranium or plutonium.
Deuterium is hydrogen with an extra neutron, and tritium is 3 neutrons. Why does hydrogen get special names for its isotopes? Does anything else get special name? Why isn't it just called hydrogen 2 or hydrogen 3? Aura, because it's special. There's too many to name for the others, because there's a lot of it in stars. Hydrogen is a special little guy. Okay.
The critical development was the immensely high temperatures generated by a runaway chain reaction. This is why devices that generate large fusion reactions through high temperatures are
able to just sit there and absorb all this from nothing? Probably not, but I've learned all of this in the past, so this is just, if anything, it's a refresher. I'm aware of like most of the concepts. And then if I don't remember all of it now, I'll know when I read something in the future, it'll click, and then, I don't know. We'll do it. After this, we'll do a ChatGPT 20 question quiz, okay? Just for you guys, all right?
called thermonuclear weapons. The more colloquial name is the hydrogen bomb, as the ordinary fusion fuels, deuterium and tritium, are isotopes of hydrogen. By 1952, work was well underway on the development of a thermonuclear device. The main challenge was developing a form of deuterium and tritium that was stable in a solid form, as both are gases at normal temperatures and pressures. Edward Teller, known as the father of the hydrogen bomb, and other scientists at the US Atomic Energy Commission decided upon a proof of concept. His configuration for a thermonuclear weapon, called a Teller-Ulam design, uses the energy of a fission bomb, the primary, to compress and heat the secondary, a container of fission fuel. The immense heat generated in the secondary then causes a large number of fusion reactions to occur, greatly increasing the yield of the weapon. Because the fusion reactions generate neutrons of extremely high energy, these can be used to initiate fission in U-238, meaning a tamper made out of natural uranium will increase the blast yield further. Therefore, most hydrogen bombs are more correctly described as fission, fusion, fission weapons. Typically, fission and fusion account for roughly equal amounts of the yield. The exact process which leads to the compression of the secondary is still a matter of conjecture, but the most likely explanation is tamper ablation. When the primary detonates, an enormous amount of high-energy X and gamma-ray radiation is released. This heats the outer shell of the tamper to such a high temperature that it evaporates, which accelerates the tamper inward, compressing the fusion fuel. The first major challenge in the development of the hydrogen bomb was the hydrogen itself. Deuterium and tritium are gases, and tritium is both radioactive and has a reasonably short half-life. But for a proof of concept, it was decided to simply use liquid deuterium, which had to be cooled.
What is it when something is radioactive? When we say that, is that just a colloquial way of saying that it undergoes radioactive decay at a decently high rate? Whatever the fuck that means? Is that what it means when we say something's radioactive? Does it have to be a certain type of decay, or is it any type of decay? How do you call something? Because everything decays. Everything has a half-life, right? How radioactive something have to be to call it radioactive? How radioactive does something have to be called radioactive? Okay, no, I don't care. Stable elements never decay. Wait, is that true? Do stable elements decay? No, they don't. Have nuclei that are not radioactive and do not spontaneously undergo radioactive decay. Oh, just kidding, loser. At least some stable isotopes, possibly all stable isotopes, do undergo the same decay of radioactive isotopes. The rate at which they undergo the decay is so slow as being consequential are immeasurable. It's longer than a few billion years are considered stable. Oh, okay.
To cryogenic temperatures. The first shot of Operation Ivy, undertaken in the Pacific Proving Ground, the Ivy Mike device, was therefore not a deliverable weapon. It weighed some 74 metric tons. The device was encased in a 6-meter high, 2-meter wide steel tube with 30-centimeter thick walls. This assembly, which itself weighed some 49 tons, would then be filled with liquid deuterium. At the top of the tube sat the fission primary, the Mark V fission bomb, a more efficient version of the Fat Man device with a composite plutonium-uranium pit. The primary and liquid deuterium were separated inside the device itself, with the secondary surrounded by 4.5 tons of natural uranium which acted as a tamper. To support the refrigeration equipment, a 3,000 kilowatt power plant was installed, and the whole assembly was housed in a 20-meter high building called the Shot Cab. It really was more of a nuclear installation than a nuclear weapon. The energy released by Ivy Mike was truly terrifying. Mere moments after detonation, a 3-mile or 5-kilometer wide fireball engulfed the test island, triggering lightning strikes and sending detectable shockwaves around the Earth. The mushroom cloud rose to an altitude of 50,000 feet in just 90 seconds. On board ship, the observers from the Naval Task Force were shocked by the heat radiated from the fireball. One described it as frightening, despite being stationed some 40 miles away. 30 minutes after detonation, the diameter of the mushroom cloud was 60 miles, and it only stopped rising once it hit the tropopause at an altitude of 120,000 feet.
60 miles? What was the name of this weapon again?
All that was stopped rising 30 minutes after. One described it as frightening. It was from the Naval Task Force with 1,000 feet detectable shock. It really was more, and the whole assembly was housed in a 20 troops to an altitude of 50,000 feet in just 90 seconds. On board ship, the observers from the Naval Task Force were shocked by the heat radiated from the fireball. One described it as frightening, despite being stationed some 40 miles away. 30 minutes after detonation, the diameter of the mushroom cloud was 60 miles, and it only stopped rising once it hit the tropopause at an altitude of 120,000 feet. All that was left of the test site was a 1.9 kilometer wide crater. Later calculations placed the yield produced by Ivy Mike at 10.4 megatons of TNT.
Jesus.
10,400,000 tons of trinitrotoluene. To put that into perspective, the Great Pyramid of Giza weighs approximately 2.3 million tons. Thus, to make an explosion as powerful as Mike, you would need to make 4 piles of high explosive as large as the Great Pyramid. Humanity truly had entered a terrifying...
Thank you. For all of us who have seen the Great Pyramids, now I can intuitively understand how much TNT that is.
...a new technological age. With this horrifying demonstration of the destructive potential of thermonuclear weapons, the species itself now possessed the technology required to commit autogenocide.
Thanks.
But Ivy Mike was never really designed to be a deliverable weapon, and although a number of weapons were jury-rigged together, called the Mark 16 nuclear bomb, these were immensely impractical. Somehow, a solid fusion fuel had to be developed in order to allow for the deployment of practical, deliverable thermonuclear weapons. An answer was found in the chemical element lithium. It was well known that when the isotope lithium-6 is hit with a neutron, it can undergo fission. It is the only light element which can do so, but the energy released in this process is much smaller than uranium. But of more interest is lithium-6's fission products, helium and tritium. The ability to create tritium by exposing lithium-6 to the intense neutron radiation of a fission bomb detonation was the key breakthrough in hydrogen bomb design. All that was required to sustain fusion was the deuterium, which was simply chemically bonded to the lithium atom to create lithium deuteride. Much like lithium hydride, lithium deuteride is a stable, inert, inorganic solid at room temperature. It has a melting point of nearly 700 degrees Celsius and is not radioactive. Just as black powder contained everything required for a deflagration in a single, stable solid, both the oxidizer and the fuel, so had Teller's team forged a fuel that contained deuterium and tritium in a solid, inert form. The first test of a solid-fueled thermonuclear device was set for March 1st, 1951. Codenamed Castle Bravo, the shot would be detonated at the Pacific Proving Ground on Bikini Atoll. The device itself, called the Shrimp, was much smaller than the Ivy Mike design. It weighed just over 10 tons. The fission primary was a variant of the compact Mark 7 bomb, which, when boosted, produced a yield of 60 kilotons. The secondary was formed by a cylinder of lithium deuteride, containing both a fission spark plug at its center and a natural uranium tamper surrounding the fusion fuel. The spark plug was a critical element in achieving a good fusion burn. Essentially a rod of weapons-grade plutonium, as this underwent compression, it would become critical, creating a fission explosion within the fusion fuel. This would act as a source of internal pressure, compressing the fuel against the imploding tamper and showering the lithium with high-energy neutrons. This whole assembly was housed in a radiation case, a 1-inch thick solid aluminium cylinder. The radiation case was designed to reflect the initial burst of X-rays, confining it for as long as possible and directing its energy towards the fusion secondary. The space between the primary and secondary was filled with a form of polystyrene foam, which would instantly turn into a low-Z plasma, allowing for a smooth transfer medium for the X-ray radiation. The yield of the weapon was designed to be about 5 megatons. However, Castle Bravo seriously overperformed. Lithium has 2 stable isotopes.
This is the Castle Bravo test? Was the year that this one was blown up? '54. Oh, good one. Holy shit, it's Gaza. Just kidding. Marshall Islands is one of those weird island countries that we memorized for the map game. It's like somewhere out here. Wait, and these people lived where? Where they got... Oh, they were on the island on the south side? Jesus. Wait, and they were 40 miles away? Am I understanding that? Thanks. Oh. I thought you gave me the wrong coordinates. Jesus. Wait, really? Jesus. Are these all nuclear test sites? Am I to assume that if there's like a big missing thing? Wait, what is this stupid fucking island? Is it just an island with a big lake in the middle, or what the fuck? It's an atoll. Are there other ones of these? These formations are common in the Pacific. Huh. Okay. Oh, look, there's more. The water in the middle is all salt water, I'm assuming, right? Okay. Holy shit, the Chernobyl sounds. Wait. What's this guy's problem? Did they scuttle this, or did he get... We sunk a lot of ships as test targets. Oh, okay. Cringe. Okay.
Lithium-6 and lithium-7. Lithium-7 is by far the most common on Earth, and it made up about 60% of the lithium in the fuel. Under normal circumstances, when hit with a neutron, a lithium-7 atom will absorb it and decay into beryllium-8, adding nothing to the reaction. What no one knew at the time was that when hit by neutrons with the kind of energies present in a nuclear detonation, lithium-7 will also undergo fission, producing both tritium and more neutrons. These reactions bombarded the uranium tamper with far more neutrons than expected, which led to much more fission. In all, these processes generated a yield of 15 megatons, quite literally 1,000 times as powerful as the little boy bomb dropped on Hiroshima. As soon as the device was detonated, the control crew knew something went wrong. The shot was fired from a concrete bunker located on NU Island at the other end of the atoll, some 38 kilometers away. When the ground shock hit, it was so powerful that standing was impossible. As a result of the overpressure, water surged out of the toilet and behind the control panel. The fireball was unimaginably huge, measured at some 7 kilometers in diameter. It was so bright that it was instantly visible on neighboring Rongelap Atoll. On board the Japanese trawler, Fukuyuru Maru, one of the sailors remarked that the sun rises in the west. Around the control bunker, all above-ground buildings had been flattened by the blast wave. As onlookers on board the Navy task force watched, the colossal mushroom cloud rose rapidly into the sky, ballooning to over 100 kilometers in diameter. Soon it began to snow. With tiny white flakes of ash raining down on them and Geiger counters rapidly clicking, the task force steamed south at full speed. Castle Bravo was a particularly dirty bomb, producing extremely high levels of fallout. For reasons that will be described later, the combination of high levels of fission in the uranium tamper and sea-level detonation generated a massive and deadly fallout plume. This was complicated by a misreading of high-level winds. In the control bunker, the scientific team led by Dr. Felt soon began to detect an alarmingly rapid increase in radiation levels outside. As the radioactive ash began to fall around them like a heavy snowfall, radiation levels inside the bunker began to rise. Despite being in a concrete building, the team was forced to move from room to room to find one with safe radiation levels. They were all forced to cram into a data processing room that happened to have a large amount of sand above it. About 12 hours later, once the outdoor radiation levels had dropped significantly, the team were rescued by helicopter. None received a dangerous level of radiation exposure. About an hour after the blast, radiation levels were so high that anyone outside would have received a fatal dose.
Damn.
As the deadly cloud was blown to the east, the Japanese fishermen on board Fukuyuru Maru had no idea of the dangerous situation they were now in. Blanketed by fallout, all received a dangerous dose of radiation, inducing burns and radiation sickness. One sailor died. The test forced the evacuation of several neighbouring atolls. Despite the dangerous overperformance of the device, Castle Bravo was a foundational step in thermonuclear weapon development. Not only was a solid-fueled hydrogen bomb now technologically demonstrated, but the possibility of using the much more common lithium-7 isotope as a fusion fuel had been discovered, something that would have remained a mystery without a full-scale test. Within months, the United States had fielded a number of operational, multi-megaton thermonuclear devices, beginning with the Mark 17 and Mark 24 freefall bombs, the latter of which demonstrated a yield of just over 13 megatons. Despite its high yield, the Mark 24 weighed a colossal 19 tons, severely complicating delivery. Essentially, only the American super heavy bombers could employ the weapon. The American family tree of super hydrogen bombs reached its apogee with the B-41. A three-stage weapon, the 10-ton B-41 had a maximum yield of 25 megatons, almost twice the energy achieved by Castle Bravo. The weapon entered service in 1963. As much as the Americans had been the pioneers of hydrogen bomb development, it was the Soviets who took the super-yield thermonuclear weapon to its zenith. Castle Bravo was a two-stage device, meaning a boosted fission primary bomb was used to compress a fusion secondary stage. This is the foundational design for all thermonuclear weapons. Nevertheless, there is no reason why you cannot add a third stage for even more yield. In a three-stage design, a fission primary compresses the fusion secondary, which then compresses another fusion stage. This design was realized in Project 202, which had a stated objective of developing a deliverable nuclear device with a yield of 100 megatons. This device was known to its developers as the Tsar Bomba, or the Emperor of Bombs. Tsar Bomba had three stages. The first was a fission bomb. The second stage actually contained a pair of small fusion charges which were placed around the massive tertiary stage. Given how large the third stage was, more energy was required to compress it to the requisite temperatures than the fission primary could provide. The second stage, by itself, had a yield of around 1.5 megatons. The detonation of the two secondary stages would provide so much radiation pressure that this would ignite the massive third stage. Lithium deuteride was also used as a solid fuel. Tsar Bomba had two yield settings depending on the configuration of the third stage tamper. If this tamper were made of lead or another nuclear passive material, the yield would be about 50 megatons. However, if the third stage's tamper was replaced with uranium-238, the yield was predicted to double. It was decided to test the device in 1961. Because of the potential for massive radioactive fallout, the lower yield configuration was selected. In any case, the possibility of the delivery aircraft escaping a 100 megaton detonation was questionable. The most remarkable thing about Tsar Bomba was the fact that it was air deliverable. Just. In order to fit the 27-ton device, the Tupolev Tu-95 had to have its bomb bay doors and fuselage tanks removed. Still, this feat stands testament to the skill and ingenuity of Soviet engineering. On October 17, the aircraft took off from its base on the Kola Peninsula and headed for the Arctic island of Novaya Zemlya. After slowly climbing to an altitude of 34,000 feet, by 11:20, the target area came into view. When released from the bomber, the weapon deployed a large parachute, a necessity if the crew were to have any chance of survival. At 11:13, at a height of 4,000 meters, detonation was initiated. Instantly, a 5-mile wide fireball lit up the morning sky. The blast wave was so powerful that it circled the Earth 3 times. Severny, an uninhabited village, was flattened by the blast wave. It was 55 kilometers from ground zero.
Damn.
The device produced so much thermal radiation that it would have inflicted third-degree burns on any exposed individual at a range of 100 kilometers.
Damn.
Despite the colossal yield of the weapon and the gigantic 95-kilometer wide mushroom cloud, radioactive fallout was minimal. In fact, radiation levels were so low that within just 2 hours of the blast, test crew were able to walk around Ground Zero. This low radioactive impact and the marked difference to Castle Bravo are due to both the low levels of fission in the weapon and the use of an airburst. These effects will be addressed in greater detail later. As impressive as these mega hydrogen bombs are, they really were not all that useful. Tsar Bomba was never a practical weapon of war. Even the American 25 megaton B-41, which was the most efficient nuclear bomb in history when mass and yield are considered, weighed some 4,500 kilograms. Realistically, a 10 plus megaton explosion is really overkill for virtually all situations in which one might want to use a nuclear weapon, and the costs you pay in mass and its impact on delivery systems are substantial. Most of these super hydrogen bombs had short service lives. Thus, in the late 1960s and 1970s, the emphasis of nuclear weapon design changed substantially. It was realized that if you could use a thermonuclear reaction to make large bombs unfathomably powerful, you could also use the same technology to make nuclear weapons much smaller and lighter, while still having very significant yields. For example, the Mark 13 bomb, a fission weapon, provided a yield of 30 kilotons. It weighed just under 3,000 kilograms, or 6,600 pounds. But by utilizing the additional yield generated by a thermonuclear reaction, the W-58 warhead had an estimated yield of 200 kilotons, despite weighing just 117 kilograms, or 257 pounds, about as heavy as a large man. The W-58 was just 1 meter in length.
200 kilotons. The Castle, this Ivy Mike, this was 15 kilotons, right? Or 10? 0.4 megatons. Oh. Kilo is... is less than megatons. How many kilotons in a megaton? Well, that's kind of weird. I thought kilo was 1,000. What does mega mean? Wait, I'm going backwards. Never mind. This makes sense. Just kidding.
This miniaturization meant that many more weapons could be delivered by a single system. But it wasn't just thermonuclear weapons that underwent a process of miniaturization. Within the first 5 years of nuclear weapon development, much smaller yield devices were produced. For example, the very early Mark IV bomb, which still used much of Fat Man's fundamental design, had several low-yield variants, including 1 and 8 kilotons. This lower yield was achieved by utilizing a smaller plutonium pit. Both the Soviets and Americans quickly realized the limitations of high-yield weapons in battlefield applications. When using a nuclear device tactically, meaning targeting an enemy's military forces whilst they are deployed, and therefore actually in the battle space, lower-yield weapons are far more useful. Even 20 or 30 kilotons may pose significant risks of not only collateral damage to nearby civilian infrastructure and population, but your own forces. The thing about battle is typically friendly formations will be operating in close proximity to the enemy, making a 1 megaton weapon essentially useless. This led to a divide between tactical and strategic nuclear weapons. In simple terms, tactical weapons are designed to be used on the battlefield to engage military targets in close proximity to your own forces. They are designed to win battles. Strategic nuclear weapons were designed to destroy your enemy's ability to wage war itself, either by destroying their critical military infrastructure in their home area, or, at the most extreme case, by striking their population centers and economic assets. In the early to mid-Cold War, tactical nuclear weapons were, generally speaking, smaller, lighter devices with a yield that was less than 20 or 30 kilotons. Although when defining a nuclear weapon as tactical or strategic, there is no hard line when it comes to yield. Some weapons can serve in both roles. What really makes tactical weapons different is their method of delivery. Modern battle is fluid. Opportunities for the employment of a nuclear weapon on the battlefield may be fleeting. As an example, as a NATO corps commander, you may only have an hour or two's warning that a Soviet armored division has concentrated its forces for an attack. Therefore, these small, light weapons, with low enough yield that they can safely be employed in close proximity to your own forces, need to be delivered by systems that are flexible and responsive. ICBMs, generally speaking, are not great delivery systems for tactical weapons because of the complex command and control arrangements. That makes platforms like tactical fighters, short-range ballistic missiles and artillery perfect delivery systems for tactical nuclear weapons. The most famous tactical nuclear weapon is probably Atomic Annie, an 11-inch artillery system that fired a 50 tactical weapons and revealed that they concentrated its forces for an attack. Therefore, these small field may be fleeting. Battle is fluid. Opportunities for the employment of a nuclear weapon on the battlefield may be fleeting. As an example, as a NATO corps commander, you may only have an hour or two's warning that a Soviet armoured division has concentrated its forces for an attack. Therefore, these small, light weapons, with low enough yield that they can safely be employed in close proximity to your own forces, need to be delivered by systems that are flexible and responsive. ICBMs, generally speaking, are not great delivery systems for tactical weapons because of the complex command and control arrangements. That makes platforms like...
Oh, because you wouldn't be able to OK an ICBM from all your like C2 in 20 minutes or whatever it goes.
Tactical fighters, short-range ballistic missiles and artillery, perfect delivery systems for tactical nuclear weapons. The most famous tactical nuclear weapon is probably Atomic Annie, an 11-inch artillery system that fired a 15-kiloton warhead. Tested during Operation Upshot Knothole Grable, Annie produced some of the most iconic nuclear test footage ever made. Once you imagine the possibility of a tactical nuclear war, where both sides refrain from striking each other's major cities or critical infrastructure, then the utility of nuclear weapons on the battlefield becomes readily apparent. Because of their very large area of effect in comparison to conventional explosives, even low-yield nuclear weapons can be of great utility simply by improving the accuracy of your systems, or rather, by mitigating a lack of accuracy. Obviously, the impact of a 10 or 15 kiloton blast on a land battle is not hard to appreciate, but nuclear weapons are just as useful in air or naval battle. Take submarine warfare as an example. If you have detected a submarine but you have not been able to fix or track it, meaning you know it's there but you don't know exactly where it is, you can't engage it effectively with conventional weapons. But if you have a nuclear depth charge, like the 10 kiloton W-44 nuclear ASROC, you will likely sink any submarine in a 3,000 meter radius. The same principle applies to surface-to-air missiles. Hitting a high-flying bomber is difficult with 1960s era technology, especially considering their defensive electronic warfare capability. Now imagine trying to stop dozens of them, all of which may be carrying nuclear weapons. Well, if you equip your Nike Hercules with a 20 kiloton nuclear warhead, you only have to get a single missile within 1,000 meters of the formation. Perhaps the most iconic tactical nuclear weapon was the M28 Davy Crockett weapon system, one of the smallest nuclear weapons ever fielded. Essentially a nuclear recoilless rifle, the Davy Crockett had a range of about 2 miles or 3 kilometers. It fired the M388 nuclear round. The warhead weighed just 34 kilograms. It was about the size of a large briefcase or watermelon. A pure fission weapon, when detonated, the M388 provided a yield of 22 tons of TNT equivalent. Pure fission weapon, when detonated, the M388 provided a yield of 22 tons of TNT equivalent. As with all low-yield nuclear weapons, for reasons that will be discussed later, the bomb's radiation was its most lethal feature, specifically its neutron flux. All personnel within a 150 meter radius would have become instant radiation casualties, with most dying within a period of minutes. Outside of that lethal radius, radiation casualties would reduce with distance, although many within 200 meters would have died later from radiation exposure. Blast effects would have been substantial over a 100 meter radius. The weapon was designed to be used in key defensive areas such as the Fulda Gap. Davy Crockett batteries would saturate these natural choke points with small nuclear blasts, creating a radioactive barrier through which Soviet forces would have to pass. The miniaturization of nuclear weapons, which was the prevalent trend throughout the last half of the Cold War, also led to the development of variable yield devices. Commonly called dialer yield, this feature allows the user to drastically change the explosive power of the weapon with the mere flick of a switch. The second generation of nuclear weapons, such as the Mark IV, also had multiple different yields, but these were determined by the size of the plutonium pit that was physically placed in the bomb prior to delivery. But the development of small thermonuclear devices allowed for much more flexibility. Take the American B-61 freefall nuclear bomb. Depending on the model, the B-61 has a number of different possible yields, ranging from 0.3 of a kiloton to 400 kilotons. For example, the Mod 3 bomb reportedly has 4 yield settings, 0.3, 1.5, 10, and 170 kilotons. To change the yield, all an operator has to do is adjust the settings of the weapon prior to the mission.
Why would you want it to be less powerful? So you don't upset your mom. So you can control how big the explosion is, how close the enemy forces are? I don't know.
Internal components have to be replaced. Dialer yield works by deliberately causing the weapon to malfunction at different stages of the process, or in other words, by intentionally causing a fizzle. For the Mod 3 bomb, the full yield is 170 kilotons, but we can surmise that the 10 kiloton setting is simply the yield produced by the fission primary. By changing the internal geometry of the weapon, the secondary will not be properly compressed, preventing ignition. The lower settings are achieved by intentionally causing the primary to fizzle, either by not boosting the weapon or by varying the neutron reflectors and ignition timing to only generate a partial detonation. This allows for great flexibility in the utilization of a nuclear stockpile. A single weapon, such as the sub-1,000-pound B-61, can be used to strike many different kinds of targets which require different yields. This makes them useful in both the tactical and strategic roles. Most modern nuclear weapons include a variable yield function. Both the United States and Soviet Union invested heavily in tactical nuclear weapons, which made up a large portion of their massive 30,000 weapon-plus stockpiles. Nevertheless, many have argued that even the smallest use of nuclear arms would inevitably result in total nuclear annihilation, meaning a tactical nuclear war is quite literally impossible. However, the inevitability, or not, of this proposition remains unsolved. Obviously, the employment of small-yield tactical nuclear weapons against military targets poses a very significant risk of escalation to the strategic level. Nonetheless, like many things in history, perhaps we should not treat this kind of escalation as inevitable. Historically, there have been other norms that have held in war. During the Second World War, all of the major powers possessed vast chemical weapon stockpiles. By the development of nerve agents like sarin, Germany had achieved a technological lead, although Britain had large stockpiles of mustard gas. Despite the ability of both sides to use chemical weapons on enemy population centers, and despite the fact that all sides were engaged in a total war, one in which national survival was at stake, neither the Germans, nor the Western Allies, nor the Soviets employed these devastating weapons. Indeed, although there were instances of chemical weapon attacks on the Chinese, chemical weapons were not used in the Pacific Theater either. Even though Japanese and German cities were being turned into rubble by Allied bombers, they still refrained from using this most terrible of weapons for fear of retaliation in kind. When it came to chemical weapons, a form of mutually assured destruction existed. This historical episode should guide us when we consider the employment of nuclear weapons. Clearly, if the major powers could refrain from employing chemical weapons in a total war, then we should conclude that it is at least possible for a war between NATO and the Soviet Union to have involved only a limited nuclear exchange. Certainly, both powers had to be prepared for that possibility, which is why they invested so heavily in low-yield tactical weapons. In many ways, the ballistic missile revolutionized the nuclear bomb, at least in the strategic role. Indeed, an evaluation of the nuclear weapon itself is incomplete without considering its method of delivery. After all, a 100 megaton hydrogen bomb is perfectly useless if it cannot be delivered to the target. Throughout the first decade of the nuclear age, the immense weight and size of nuclear weapons meant the heavy bomber was the only practical delivery system, giving the United States a significant advantage throughout the 1950s. Nonetheless, the Soviets were about to change the game. On the 12th of September 1960, the R-7A was declared operational. With a total range of over 9,500 kilometers, this liquid-fueled rocket could launch a nuclear weapon directly from the Soviet Union to North America. The intercontinental ballistic missile was born. By the mid-1960s, both the United States and Soviet Union had a significant ICBM capability, especially with the introduction of the American Minuteman I solid-fuel missile in 1962 and the Soviet R-16 a few months earlier. Both powers were now faced with the possibility of a massed, intercontinental ballistic missile strike. Within 40 minutes from the order to launch, dozens of thermonuclear warheads could be impacting all over the country. This was especially concerning if an enemy launched an attack on your nuclear capability. With such unimaginable offensive firepower available, your entire nuclear arsenal could be wiped out in a matter of hours. Strategic bomber airbases, ICBM missile silos, command and control facilities, and nuclear stockpiles. These could all be struck with 3 to 5 megaton nuclear weapons in a matter of minutes. Such an operation is called a counter-force nuclear strike, and ICBMs made it a realistic possibility. Such a capability was very destabilizing. If either side thought they had a realistic chance of effectively crippling the other's nuclear capability, the chances of a nuclear war grew substantially. In essence, the ICBM incentivized both sides to strike first. Although a counterforce strike somehow seems less morally challenging than targeting enemy population centers, which is called a counter-value attack, the level of collateral damage would still be enormous. Striking enemy missile silos, which are hardened, underground structures, requires powerful surface bursts. In the United States, these are located in Montana, Colorado, and North Dakota. The resulting fallout, which would disproportionately impact the Midwest, would lead to millions of casualties. This threat of a successful, counter-force nuclear attack carried out by intercontinental ballistic missiles led to the development of something called the nuclear triad. Although the origin of the nuclear triad can certainly be partially explained by inter-service rivalry, as both the US Navy and US Air Force fought for the primacy of their own nuclear delivery systems, it soon became the cornerstone of US strategic deterrence. The US nuclear triad included ICBMs that were fast and accurate, strategic bombers that were flexible, and nuclear submarines that were survivable. The primary idea was to ensure that a Soviet counter-force strike would not be successful by diversifying launch platforms and keeping both submarines and bombers constantly deployed. To fulfill this requirement, throughout the 1960s, US Strategic Air Command kept 12 flights of nuclear-armed B-52s constantly airborne. Codenamed Operation Chrome Dome, this ensured that even if air bases were struck by ICBMs, a significant amount of strategic air power would be able to rapidly respond. It also improved the United States' first strike capability. The final element in the nuclear triad were the United States Navy's George Washington-class nuclear submarines, which deployed the Polaris ballistic missile. With a range of nearly 5,000 kilometers and equipped with...
Do you touch type? No, I usually just type with my mind.
3 W-58 200-kiloton warheads, each Polaris missile could devastate a city. However, the weapon lacked the accuracy to hit point targets, with a circular error probable of some 900 meters. This meant the Polaris was only really a counter-value weapon designed to target enemy population centers, making it a second strike weapon. Having 3 200-kiloton W-58 warheads allowed for much greater destruction of value targets than the single W-47 600-kiloton device. This is because of the way blast scales, which is different to the destructive radius. Blast energy is expended in 3 dimensions, but a city is basically a 2-dimensional object. Therefore, by hitting a soft target like a city with 3 smaller warheads, a far greater area will be subjected to higher blast overpressures, increasing the total damage inflicted. In effect, a larger area would be closer to one of the 3 smaller epicenters. With such a capability hidden under the oceans, a first strike would, hopefully, be perpetually deterred. Because of their inherent stealth and survivability, the ballistic missile submarine remains the premier arm of strategic nuclear deterrent. The United States, Russia, China, Great Britain, France, and India currently deploy nuclear weapons on ballistic missile nuclear submarines. With the next generation of missiles such as Trident, they also became a potent first strike weapon. The Trident D5 has a range of more than 12,000 kilometers and delivers a payload of 14 warheads or dummies over that distance, although it is limited to 8 warheads by treaty. Currently armed with the 475 kiloton W-88 nuclear warhead, the Trident can attack 8 individual target sites over a very wide area, perhaps 1,000 kilometers. This is called a Multiple Independent Reentry Vehicle, or MIRV, capability, and it is the current state-of-the-art in ballistic missile nuclear delivery systems. Russia, China, Great Britain, and France field MIRV-capable systems. With the GPS-guided Mark V reentry vehicle, the weapon has a CEP of just 90 meters, making it 10 times more accurate than Polaris. Each Ohio-class submarine deploys 24 Trident ballistic missiles, which could potentially field 192 W-88 warheads, providing a combined yield of 91 megatons. Although, in reality, the smaller 100 kiloton W-76 is probably deployed in large numbers. There are 14 Ohio-class SSBNs currently operational. Russia has a comparable capability with its Typhoon and Boreas classes. It is a truly awesome and terrifying concentration of destructive potential. With these capabilities in place, a mutually assured destruction exists between the major nuclear powers, as ballistic missile submarines have made a completely successful counterforce strike almost impossible. Any large-scale nuclear attack will always be able to be met in kind, and by this means peace can be maintained, but only at the end of a loaded gun. Even at its currently reduced levels, a mass strike by Russia's high-readiness nuclear forces on the United States would inflict approximately 100 million casualties. So, what actually happens when a nuclear device is detonated? Let's imagine a 1 megaton nuclear bomb is triggered a few thousand meters above the Earth's surface. As the detonation system triggers the fission primary, the plutonium pit is highly compressed, making it supercritical. The immense energy released by the primary compresses the secondary, leading to both fusion in the lithium deuteride fuel and fission in the uranium tamper. As explained previously, the initiation of a nuclear chain reaction in a weapon generates a vast amount of energy in a small concentration of matter. This leads to the near instantaneous generation of extremely high temperatures and pressure. At the moment of detonation, conditions within the bomb itself are analogous to the center of the sun. Tens of millions of degrees and over 1 million atmospheres of pressure. The extreme temperature instantly vaporizes the bomb and all of its components, including the uranium or plutonium, casing, and fission products. These gaseous weapon products contain a vast amount of kinetic energy and begin expanding at extremely high velocity. Because of the temperature of the weapon components, within less than 1/10 of a millionth of a second, they will begin to emit copious amounts of high-energy electromagnetic radiation, primarily in the form of X-rays and gamma rays. This wavelength of electromagnetic radiation is absorbed rapidly by the atmosphere. This initial burst of X-ray radiation may only travel a few hundred meters. The process of X-ray absorption rapidly heats the air to a point that it begins to radiate, forming a spherical area of luminescent air and gaseous weapon debris. Anything within this region will be vaporized. This area is called the fireball. The fireball itself is so hot that it releases vast amounts of energy as ultraviolet, visible, and infrared light. This is why nuclear explosions have their trademark bright white flash, which is a way you can distinguish a nuclear detonation from a very large conventional explosion. At just 1 millisecond after our 1 megaton detonation, the fireball will be so luminous that it will appear brighter than the noon sun to observers 100 kilometers away. The radiant heat emitted by the fireball is enough to cause third-degree burns and start fires at several tens of kilometers. The size of the fireball and the total amount of thermal energy released is directly proportionate to the weapon's yield. As the fireball is formed, it rapidly expands until it eventually reaches its maximum diameter, which is determined by its temperature. This extremely rapid expansion, combined with a very high temperature, generates a wall of highly compressed air that radiates out from the explosion. Traveling faster than the speed of sound, this wall of high-pressure air is called the blast front or blast wave. Any above-ground structures will experience immense pressure as the blast wave passes over them, as any difference in air pressure between different parts of the structure will exert a force on the structure as a whole. This means buildings can be demolished just by the passage of the blast wave itself if the pressure is high enough. At the front of this blast wave is an area of peak overpressure, after which the air pressure drops off substantially. The passage of the blast wave is accompanied by very strong winds, first emanating out from the epicenter and then, as an area of negative pressure follows the blast wave, towards it. The strength of the wind is proportional to the level of peak overpressure. It is important to note that these winds are local and therefore do not contain any radioactive material. As the blast front radiates out from the fireball, it steadily loses strength.
Holy shit, it's like when Kenshin uses his ultimate attack, and if it is blocked the first time, it sucks him back in, and then he kills him the second time. Oh my god.
Blast effects and the high-speed winds that are generated by a nuclear detonation in the lower atmosphere are the primary mechanism by which nuclear weapons kill people and destroy things. As the fireball reaches its blast effects and the high-speed winds that are generated by a nuclear detonation in the lower atmosphere are the primary effects. As the blast front radiates out from the fireball, it steadily loses strength. Blast effects and the high-speed winds that are generated by a nuclear detonation in the lower atmosphere are the primary mechanism by which nuclear weapons kill people and destroy things. As the fireball reaches its maximum radius, it instantly begins to rise. Just like a hot air balloon, there is a substantial difference in pressure between the fireball itself and the cool air surrounds it, which causes it to rapidly ascend. As the sphere rises, it cools, allowing the vaporized material to condense to form a cloud containing small particles of weapon debris, including highly radioactive fission products, and water vapor. As this spherical cloud rises, the outer edges drag on the atmosphere, slowing them down. This causes the cloud to change shape, from a sphere to a toroid or donut. As it ascends, this cloud undergoes a violent horizontal circulation, which generates a strong updraft at its center. These powerful winds suck dirt and debris up from the surface, connecting the rising cloud to the ground, giving rise to the iconic image of the nuclear age, the mushroom cloud. The huge temperature differences between the cloud and the atmosphere will cause it to reach an enormous height, potentially 100,000 feet, and
True. Just so you get both sides, because I don't want to be partisan here.
U.S. military was basically faking these bomb tests to freak out the Russians.
How did they fake it?
They just did, yeah, exactly.
This is
exactly.
it?
Well, so there's a, yeah, okay, so here's the question, right? So what happened, okay, so this is great. Okay, you'll love this. So what happened to the camera?
You son of a bitch. You son of a bitch. What happened
How
to
is
the
that happening yet the camera is like totally stable and fine?
Oh my god.
And by the way, and the film is fine. Well, and by the way, okay, we'll do this one. We'll do the loop one more time here.
It showed
So
up.
wait a minute. First
It
of all,
wasn't there.
First of all, where'd the car
No
come
car.
from?
No car.
Second is, does it really look like a
Car.
real, does that look like a real car?
That's insane. The fucking car. Wow.
Wow.
Okay, we'll do this one. We'll do the loop one more time here.
It showed
So
up.
wait a minute. First
It
of all,
wasn't there.
first of all, where'd the car
No
come
car.
from?
No.
Oh my god, guys. How did cameras survive nuclear tests? On the face of it, this is a compelling question. How is it possible for something as delicate as a camera to survive the apocalyptic destruction of a nuclear explosion, especially ones built decades ago? The origins of this latest exercise in distrusted imagination come from an episode of the Joe Rogan Experience podcast that shows footage recorded in the 1950s of nuclear explosions destroying buildings, houses, and cars. In the commentary, the billionaire investor Mark Andreessen questions the footage's validity by drawing attention to some peculiar features, not least the camera's ability to survive the blasts. Shows had a big impact the day after it was released. A post on Facebook, quoted by Reuters, shared the footage and, and asked, why aren't the cameras in these videos of the test nukes blown up with houses? The person who posted it then leaps to sadly predictable conclusions at speeds that would make the explosion blush. It feels like we've been lied to and psyoped for decades on this subject. They add that this also questions the reality behind Hiroshima and Nagasaki because people are living there today despite the nuclear fallout. Sure, the cameras used to film the tests that have recently fallen under scrutiny were specially designed to withstand the explosions. They were encased in steel and lead and positioned on towers secured in concrete. All this information is available in declassified military documents that you can read for yourself. In 1955, in what is called Operation Teapot, 48 cameras were set up at distances that ranged between 838 and 3,200 meters away from ground zero, the site of the explosion. These cameras were all protected. Those directed at the exterior buildings were put on towers embedded in concrete at heights that helped minimize interference from dust and debris. Technical photography. Page 13. Wait. Wow, cute. Crazy how all this information is available online if you're just willing to look for it, huh?
Increased to a very large size. The highly radioactive fission products and other elements of the bomb are all contained within the head of the mushroom cloud. Generally speaking, these vaporized weapon debris condense into tiny particles. By themselves, they will be elevated into the stratosphere and dispersed over a large area, diluting their effect. For example, because both detonations were airbursts, not a single injury was sustained from nuclear fallout in both the Hiroshima and Nagasaki nuclear attacks. However, if the fireball comes in contact with the Earth's surface, large amounts of dirt, dust and rock will also be vaporized and mixed into the fireball itself. When these condense into solids, they form much heavier objects, to which the highly radioactive fission products become attached. When the updraft weakens as the cloud cools, these heavy pieces of debris fall back to Earth in concentrated areas. We call this phenomenon nuclear fallout. Nuclear detonations can also induce powerful disruptions in electric and magnetic fields, which, although harmless to biology, can negatively impact unshielded electronics. This phenomenon is called an electromagnetic pulse, or EMP. For detonations
That's why I always buy the $100 HDMI cables.
near the Earth's surface, this effect is caused by an area of intense ionization near the burst, which generates powerful electric currents in both the air and ground. This causes a significant drop in electromagnetic field strength, which is the most powerful near the burst. With a reasonably high yield, the range at which an EMP has an appreciable effect will be below the destructive radius of heat and blast. Nonetheless, for low-yield weapons, the EMP may outrange the blast effect. The impact of an EMP generated in the upper atmosphere is far more significant. When detonated at an altitude of 300,000 feet or more, the intense X-ray and gamma-ray flux travels much farther before the radiation is absorbed by the atmosphere. The process by which X-rays are attenuated by the atmosphere is called photoelectric absorption, where the oxygen atoms in the upper atmosphere absorb an X-ray photon and then emit an electron. This causes a rain of electrons to shower the Earth's surface, which generates a brief but intense electromagnetic field that can generate a charge in unshielded electrical conductors, damaging delicate electronics over a vast area. Computers are particularly vulnerable to EMP effects. In essence, nuclear weapons release their energy in 4 ways: blast, radiant heat, initial radiation, which is defined as radiation given off by the weapon in the first minute after detonation, and residual radiation. About 50% of the energy is converted to blast, 35% is emitted as thermal radiation, which is primarily ultraviolet to infrared light, 5% as initial radiation, and 10% as residual radiation. Obviously, these numbers describe a detonation in the lower atmosphere. As most of the weapon's energy is converted into the blast wave, and the majority of human structures and vehicles are most susceptible to blast effects, maximizing the blast pressure is a key principle of nuclear weapon deployment. The blast itself is best described as a very short but intense region of overpressure. It is essentially a wall of highly compressed air, which is followed by steadily decreasing pressure levels after its passing, including an area of negative pressure where air is being sucked back towards ground zero. The passage of the blast front is accompanied by very strong winds, which can be almost 300 miles per hour with a peak overpressure of 10 psi. The higher the peak overpressure, the faster the blast front will move. It can travel at several times the speed of sound in a high-energy detonation, although as peak overpressure drops with distance, so does the speed. Maximizing blast pressure is the primary reason why airbursts are utilized. If detonated above a target rather than on it, very little of the blast energy will be transmitted to the ground. Additionally, when a nuclear weapon detonates in an airburst, a larger area will be subjected to the blast front. If the height of the airburst and the yield are carefully managed, then a number of blast phenomena can be leveraged to greatly increase the power of the blast wave. The first is something called a Mach stem. Upon detonation, the blast front radiates out from the fireball in all 3 dimensions. When it strikes the ground, it is reflected, creating a second blast front that also radiates out in 3 dimensions. As the 2 blast waves move away from ground zero, the reflected wave begins to overtake the incident or original blast wave. When this happens, there is an area close to the surface where both blast waves merge into one, more powerful blast front. This area is called the Mach stem, which will produce significantly greater overpressure. The second blast phenomenon provided by an airburst is something called a precursor. Discovered in the Grable shot of Operation Upshot Knothole, made famous by the use of artillery as a nuclear delivery system, the low blast height and dusty desert environment led to the formation of a superheated layer of air right on the surface. The lower air density allowed for the formation of a precursor wave that travelled in front of the max stem. This reduced the peak overpressure of the blast wave, but greatly increased the dynamic pressure, meaning more powerful winds. This greatly increased the damage to drag-sensitive targets. Generally speaking, if you are attacking a soft target, such as a city or a military formation, airbursts are preferred. Nonetheless, there are many scenarios which require a surface burst. Hardened targets, such as bunkers or hardened concrete buildings, can withstand relatively high overpressures, especially if a facility is housed underground. For an underground bunker or missile silo, the thermal radiation and overpressure of a nearby airburst may not pose a substantial threat. Nevertheless, these structures are vulnerable to energy transfer through the Earth itself, referred to as a shock front as opposed to a blast front. Whenever a nuclear weapon is detonated on the surface, just below it, or at a low enough altitude that the fireball comes into contact with the ground, this is called a surface burst. Surface bursts will tend to leave craters. When a weapon's energy is transferred to the Earth directly, this induces an effect that is very similar to a major earthquake, at least in the local vicinity. This can cause the internal collapse of deep underground facilities, and if close enough to the surface to be within the volume of the crater, they will be annihilated. A similar utilization of blast energy can be leveraged underwater. Just as with conventional explosives, water is an excellent conduit for kinetic energy. In water, the shock front behaves very similarly to the blast front in air, radiating out in all directions. However, with an underwater burst, the peak overpressure will not diminish with time in the same way as in air. This gives an underwater burst a much greater range of effect in terms of shock and blast. For example, at a range of 1,000 meters from a 100 kiloton burst, the peak overpressure in air might be 5 pounds per square inch. In water, at the same range, it will be 2,700 psi. This makes underwater bursts especially deadly to submarines.
Damn.
As noted earlier, in an air burst, almost half of the bomb's energy will be released as heat or thermal radiation. This is caused by both the absorption of X-ray radiation by the atmosphere and the massive kinetic energy of the bomb products, which serve to heat a spherical region of air until it becomes incandescent. This is the fireball. The fireball gives off an extremely large amount of thermal radiation, but the total amount will depend on the burst height, with an airburst illuminating the largest area, the yield of the weapon, the distance from ground zero, and, to some extent, the atmospheric conditions. The fireball emits energy in the ultraviolet, visible, and infrared spectrums, although the ultraviolet is mostly absorbed by the atmosphere. The thermal energy drops with distance. In a 1 megaton airburst, everything within a 10-mile or 16-kilometer radius would receive 3 calories per cubic centimeter of exposure, enough to cause moderate flash burns and ignite some material. Closer in, at a range of 5 miles, that exposure climbs to 25 calories per cubic centimeter. This thermal radiation has 5 miles, that exposure climbs to 25 calories per cubic centimeter. This thermal radiation has 2 destructive effects. The first is its impact on people. Anyone who is directly exposed to the fireball and within a dangerous range will receive potentially fatal burns. If someone is close enough to the burst, they may well be vaporized. The second destructive effect is fire. Exposed flammable materials will ignite if they absorb enough thermal radiation. When combined with the destructive impact of the blast, these fires can lead to a firestorm amongst the rubble and destroyed buildings. In Hiroshima, the little boy caused a comparable amount of fire damage as a conventional bomber strike with about 1,000 tons of incendiary bombs. When you consider how low the yield was, the destructive potential due to fire alone is readily apparent. About 5% of the bomb's energy is released in something called the initial radiation, meaning the ionizing radiation released by the weapon in the first minute after detonation. The reason 1 minute is the appropriate time period for describing the initial radiation effect is simply because the mushroom cloud will be high enough that no radiation will reach the ground after 60 seconds. This is true for all yields, as hotter mushroom clouds rise faster. Technically, ultraviolet and infrared light are forms of radiation, but they are not ionizing radiation, meaning they lack the energy to ionize atoms and therefore alter chemical bonds. Ionizing radiation can cause significant damage to living cells, leading to radiation poisoning, a higher risk of cancer, and even death, depending on the dose. There are 4 kinds of ionizing radiation. Alpha particles, which are essentially just the nucleus of a helium-4 atom, beta particles, which are high-energy electrons or positrons, neutrons, and gamma rays. Alpha and beta particles have a very short range in air, and thus none of this form of radiation will reach the ground from an airburst. This leaves us with 2 forms of relevant initial radiation. The first are gamma rays. Basically light with photons of extremely high energy, gamma rays are emitted in the initial reaction itself and by nuclear processes that occur immediately after it. They are also released by the rapid decay of fission products in the mushroom cloud itself. The second form of relevant initial radiation are neutrons. The fission and fusion reactions themselves generate a vast neutron flux which radiates out in all directions. Both gamma ray and neutron exposure are extremely dangerous to humans at high doses. In general terms, for a typical high-yield device, the gamma ray emission will far exceed that of neutrons, which account for only about 1% of the bomb's total energy. Both gamma rays and neutrons are very difficult to shield against. For example, at a distance of 1 mile or 1.6 kilometers from a 1 megaton airburst, the initial radiation dose would probably prove fatal to the majority of humans that were protected by 24 inches of concrete, more than enough to shield them from thermal radiation at that range.
Damn.
In comparison to gamma rays, neutrons have one important feature: they can make other materials radioactive. When exposed to a neutron flux, some of the atoms on the target material will capture a neutron, creating a heavier isotope. These are generally unstable and will undergo radioactive decay, emitting gamma radiation or alpha and beta particles. With all that being said, in a high-yield nuclear detonation, the initial radiation is very unlikely to cause large-scale injuries or death. That is because both gamma rays and neutrons are absorbed by the atmosphere at a much higher rate than thermal radiation or blast, giving them a much shorter range. As an example, in order to receive a dangerous dose of 300 rads of initial radiation from a 1 megaton airburst, a person will have to be 3,000 meters away from ground zero. At that range, they will be receiving 1,000 calories per cubic centimeter of thermal radiation, 30 times the level at which burns can occur, and experience peak overpressure of 10 psi, enough to destroy reinforced concrete buildings. In essence, for a high-yield burst, with the exception of individuals who are heavily shielded, if you are close enough to the fireball to receive a dangerous dose of initial radiation, you have almost certainly been killed by heat and blast. This relationship is inverse for lower-yield weapons, however. For the 15 kiloton burst experienced by Hiroshima, the 300 rad radiation dose occurs at 1,600 meters.
Okay, these are like effects of a nuclear blast. We don't care as much about these.